Thank you everyone for taking the time to attend this webinar. We're going to go through an overview of Amazon Aurora with Postgres compatibility and get into some details on the architecture and the performance, as well as a few other features related to the overall product. And so I'm going to start by talking a little bit about why we built the Aurora project in the first place, and then go into specifics about Postgres compatibility that we have added, and dive deeper into the architecture, and then get to a few specific things about performance monitoring and data migration. And then we'll end with a few questions. But first, to set the stage, I want to talk about the history of Amazon RDS. And RDS, of course, stands for Relational Database Service. And before we talk about that, of course, we have to talk about the beginning of AWS. So AWS was launched way back in 2006 with our very first service, Simple Storage Service, or what most people call S3. 3 years later, we first launched RDS, with the first relational database engine we supported in RDS being MySQL. And 3 years after that, we added support for Oracle and SQL Server in RDS. And then we added support for Postgres in 2013. Now, up to this point, we were managing other people's engines in RDS, whether it's open source engines or the commercial engines from Oracle and Microsoft. But in any case, we were providing managed database services to automate a lot of the simple repetitive tasks that DBAs do. The overall benefits of RDS is what we're delivering for other people's engines. But in 2014, we announced the Amazon Aurora project. And this came from customers who were seeing these different database engines in RDS and seeing the different capabilities between the commercial and open source engines. And they're asking us for a combination of the capabilities that they liked in the commercial engines combined with the simplicity and cost effectiveness of the open source engines. And so we started to think about that project and came up with Amazon Aurora. And of course, I'm going to get into a lot of details on what the Aurora project is all about. But just a little more history first. We announced Aurora in November 2014, and the MySQL compatible version of Aurora went GA in July of 2015. And then, I don't have it on the slide here, but in November of 2016, we announced plans to add Postgres compatibility, and October 2017, we actually went GA with Amazon Aurora with Postgres compatibility. And so why did we do this whole Aurora project? Where did that really come about, and what does it look like? Well, as I said, customers kept on asking us for this combination of capabilities, and that caused us to take a hard look at how relational databases are built, how traditional, the traditional legacy database systems that we're all familiar with, how they're built. And they're all built pretty much the same way, with a monolithic stack of functionality, pretty much layered like you see on the slide, where there's always a query optimizer, a SQL query optimizer at the top. Then there's a layer to manage transactions. There's usually a caching layer for performance, and a logging layer and a storage layer down at the bottom of the stack. And when people try to scale this architecture, they'll take one of 3 different approaches. They might try to do sharding, where you effectively split up your database based upon, say, a customer ID or a region or some other sharding key. And this requires, of course, the application to understand the sharding. So you have to do some work to modify your application, and now you have your data spread across multiple databases, which can add complexity to the environment. Another approach is to use distributed database capabilities like two-phase commit to try to scale. The problem with that is it functionally works, but two-phase commit doesn't scale well at all in terms of performance. And a third approach is to do a bunch of fancy science to use shared storage and do some fancy work to do some shared caching across multiple servers, and to have a small army of DBAs dancing around the servers doing incantations to keep everything up and running. This is otherwise known as Oracle Real Application Clusters or Oracle RAC. And this approach can work, but it's really complicated, and it works only when you get things just so. As soon as the workload changes, you have to go change a bunch of detailed arcane configuration parameters. All of these approaches are really limited by the fact that they're trying to scale that traditional monolithic architecture. And so we decided, well, why don't we rethink all that rethink that architecture. What if we were actually inventing the relational database from scratch today, and we were inventing it for the AWS cloud? Well, if we took that approach, we would break apart that stack. We would no longer keep it in that monolithic silo. And we'd build a service that could scale up and scale out, that was self-monitoring and self-managing and self-healing, and that took advantage of everything else in AWS. It wasn't built as a silo, as a separate thing off in the corner. And the result of all that thinking and all that work is what we now call Amazon Aurora. And at the core of the Aurora project, what we've done is we've moved the logging and the storage layers, and to a certain extent the caching layers, separate from the upper layers of the database engine. We've made, we've implemented a cloud-native, cloud-optimized database-oriented storage system, which we now call Aurora Storage. And the second major thing we did was we made sure that it's integrated with other AWS services like EC2 and S3 and VPC and other services you see on the slide, and a bunch of others you don't see on the slide, so that we're taking advantage of all the other innovation that's going on in AWS. And the third major thing we did is we made sure that Amazon Aurora is part of RDS. It is a fully managed database service, just like the other RDS engines, so that customers who use Aurora will see the same kinds of capabilities that they see from the other RDS engines. It's not a radical change in how they manage their databases. Now, we did all this initially, as I said, in 2014 with compatibility with MySQL. But from the day we announced the Aurora project with MySQL compatibility, customers were asking us to add Postgres compatibility as well. And it's clear that what was going on is customers love the idea of Aurora with MySQL. Aurora MySQL is the fastest growing service in the history of AWS, so clearly customers love it. But they also have a bunch of workloads that they think fit better on Postgres. And so they wanted us to do Aurora, it wasn't either or, they wanted us to do it for both MySQL and Postgres. And so that's what we've done with the Aurora Postgres project. Now, what are the reasons that customers want us to add Postgres? Well, this slide shows some of the reasons customers give us when they come to us and say, hey, please add Postgres to Aurora. First off, it's an open source project. It's an open source database. It's actually been in development since 1996 for more than 20 years. It's owned by a foundation, not by a company. So there isn't a company out there that you can buy that would give you control of Postgres. It's truly an open source project. The license they chose way back when is actually a very open, permissive license, which makes it easy to fork Postgres and go off and innovate and do all kinds of crazy experiments, and then contribute those experiments back if you want to. But you don't have to. And this has resulted in a whole bunch of different new features and new capabilities over the years that have come. Some have come from those forks, some have come from just people working on the core project. But the license just encourages that kind of behavior, which has been great for users of Postgres. Postgres has also had a very committed, core development team over the years. That they've always been committed to high quality of code and stability and performance. And Postgres has a reputation for stability and high performance out of the box. Postgres also has great coverage for ANSI SQL compatibility, both ANSI SQL 2008 compatibility and mostly compatible with ANSI SQL 2011, the latest update to the standard. And so in general, Postgres has a very wide and deep coverage for complex SQL, which makes it a very, very useful platform for more complex database workloads. Postgres also has really good support for geospatial capabilities with the PostGIS project, especially. And Postgres has really good support for store procedure languages, including common languages that you see here, but also its own PGSQL language, which is very similar to Oracle's PL/SQL. Now, all these factors and others are what make many customers tell us that they believe that Postgres is the most Oracle-compatible open source database out there. So customers that are looking to move their workloads from Oracle or a SQL server for whatever reason, they look for open source databases to move to, more often than not, they identify Postgres as the best landing place. So a lot of the interest we see is from customers who are looking for that kind of conversion. Now we also see data to back up that statement. So we see data from our own schema conversion tool, which can be used to convert from a source database to a target, where when customers use SET to look what it would take to move from Oracle to Postgres, they see the highest automatic conversion rates with that combination. So what have we done when we say we've added Postgres compatibility? What does that really mean? What that means is we started with Postgres 9.6.3, that specific version of Postgres. We started with that, the source code for that version of Postgres, and changed it as little as possible to integrate it with Aurora storage. So that means we're running Postgres 9.6.3 source code. We're not simulating or emulating it. And by integrating it with Aurora storage, we get the kinds of benefits you see on this slide: 2 to 3x higher throughput than standard Postgres, failover times of 30 seconds or less, durability with 6 copies across 3 AZs, and I'll show you more about that in the next few slides, and support for up to 15 read replicas with single-digit millisecond lag time. And at the same time, we are fully compatible with Postgres. It's not a compatibility layer. It's a native implementation where we, for the foreseeable future, we will maintain full compatibility with Postgres as we and the community move forward with new versions of Postgres. So let's dive into a little bit more detail on the architecture, first from a durability and availability perspective. So the Aurora storage system itself really consists of a shared storage volume that's visible across 3 availability zones to all of the instances running in a given Aurora Postgres cluster. And in a Postgres cluster, there will be one primary node that does reads and writes, and up to 15 read nodes that are read-only nodes. And those nodes can be spread across those 3 AZs, so they don't all have to be in one place. And those nodes, those instances, will be automatically managed and monitored by RDS. So if an instance fails, we will automatically replace it. If the primary node fails, then we will automatically promote one of the read nodes to be the new primary. And similarly, down at the storage layer, we're also automatically monitoring and managing the storage nodes. If a storage node fails, we'll automatically fix it and replace it. Or if a disk fails, or if there's other kinds of failures, they're all managed and monitored. So this is all part of being a managed database service within the RDS system. Now, a little more detail on that Aurora storage volume itself. Under the covers, we're maintaining 6 copies across 3 availability zones for every piece of data in your database. Now, that's not really done by replication. That's actually done by the database node itself writing log records to 6 locations. Every time you commit a transaction, the Aurora database engine will send log records to 6 locations and wait for 4 of those 6 to respond. That way, if there's outliers, we don't have to wait for all 6 of them. The 2 slowest ones won't slow us down. Those 2 slowest ones will eventually catch up, either because they eventually get to the storage nodes they're sent to, or those storage nodes will get copies from the other storage nodes. They're always talking to each other on the back end. So this gives us 6 copies across 3 AZs. On the back end of those storage nodes, we're also doing continuous backups to S3. So there's no backup window to schedule. There's no performance hit to worry about. I mentioned before we're doing monitoring and management of those storage nodes. And there's a quorum-based system for doing reads and writes. And finally, last but not least, this storage system can automatically grow up to 64 terabytes. And the limit in RDS today is 16 terabytes. So you have a lot more capacity in Aurora for larger databases. Now we can talk about failures for a second down at the storage layer. So there's different things that can fail in the storage system. Of course, a disk can fail. And it's easy to see how we replace that. We have 5 other copies of every piece of data that was on that disk. And the same is true if a storage node fails. We have 5 other storage nodes so that we can just provision a new storage node into the cluster and copy data from the other 5 to repopulate that new node. Now, if an entire availability zone fails, yeah, we've lost 2 copies out of 6, but we still have 4. And because of our write quorum, we can actually still keep running. Aurora will keep running even if an AZ fails. So, you know, it's very tolerant of failures, and all this is done automatically down in the storage layer. Now, up at the database instance layer, as I mentioned, you can have up to 15 read nodes, along with that one primary read-write node, and failing nodes are automatically replaced. If the primary node fails, we automatically promote one of the read nodes, and customers get to specify the order, as in which read node gets promoted first on failure. We also provide a reader endpoint, which allows you to balance read connections across all of your read nodes so that you can start up more read nodes when you need more capacity without changing your applications to teach them where the new read nodes are. You simply connect your apps to the reader endpoint. Now, on the back side of those storage nodes, I mentioned we're doing continuous backup to S3, both of every segment and of all the log records that apply to each segment. And these basically continuously streamed off to S3. There isn't a window to schedule and worry about the performance hit. And of course, when we need to restore, we know based on timestamps and other metadata which segments to restore, which log streams to apply to those segments, if any, to get back to the restore time that you're trying to restore to. So with Aurora, we have a different story for recovering from database crash than traditional databases. In traditional databases, you have to replay your log since the last checkpoint. And the idea is that when you do a checkpoint, you're writing all of the dirty pages from memory to storage. This guarantees that you don't have to go back further in time than the last checkpoint to recover. Of course, this means you want to have checkpoints happen fairly often so that crash recovery time doesn't take too long. The downside is that checkpoints are heavyweight and can slow down your performance. Because in a checkpoint, you're writing all those dirty pages, there's a lot of I/O to do. In Aurora, we don't ever have to do checkpoints because the storage system itself is taking the log records it receives from the database node and applying them to the database pages in the storage nodes. That means we're not doing that work in the database node, we push that work down into the storage nodes. That also means that the storage nodes are effectively always in continuous recovery, so that if there's a crash, they've already applied log records to the database pages to bring them forward in time, so there's not much work to do on crash recovery. And the way this looks, when you think about overall failover times, we can compare RDS for Postgres with Aurora Postgres. Now, RDS for Postgres is already pretty good in terms of failover times. Typically, it takes about 60 seconds or less for most failovers in our fleet. And a failover consists of failure detection, which takes 15 to 20 seconds to be sure that a node has failed and it's time to fail it over. And then when we decide to fail it over, we need to remap its name, its DNS name, to a new IP address, the IP address of the node that's going to take over. And propagation of that DNS change can take a little while, take a few seconds or tens of seconds. But in RDS for Postgres, usually that time is dominated by how long it takes to do crash recovery. Well, in Aurora Postgres, because crash recovery is so fast, this slide says 3 to 10 seconds is typically under 3 seconds. DNS propagation is the limiting factor on failover time. And so there are some things you can do with the standard Postgres JDBC drivers to make them aware of the cluster of the architecture so that they're aware of the read nodes and can figure out which read node is going to be the new read-write primary database instance. And you can actually fail over faster than DNS propagation time if you configure the drivers the right way. We have documentation on how to do that, so it's easy to figure that out. Bottom line is you can get failover times down under 30 seconds with Aurora Postgres. All right, let's switch gears a little and talk about performance. So in any software system, the way you get higher performance, well, there's two main things you can do. One is you figure out how to do less work. Figure out a better way to get the same amount of effective work done by doing less work in the computer itself. And you can see what we've done in Aurora to do that is we figured out how to eliminate a whole bunch of write IOs from your workload. By building a log structured database aware storage system, that means we only write log records and we saved all those writes. So the fastest IO you can do is the IO you don't do at all. So we do less work in Aurora, and also the IOs we are doing, we've done things to optimize how much or how little network traffic there is for those IOs. And so the other way to make software go faster, of course, is to be more efficient with things that you have to do, that you do have to do. And so as much as possible, we've made everything in Aurora asynchronous. We try to use in-memory data structures that are, for the most part, lock-free. We've tried to batch operations together to make them more efficient. And we just try to use modern software design techniques in general to make Aurora more efficient. And so to see how this really works, let's compare with the I/O traffic in RDS for Postgres with multi-AZ, and compare that with Aurora Postgres. So the multi-AZ feature in RDS allows you to just turn on this feature which will cause us to maintain a synchronous full-size copy of your database in a separate AZ, in a separate availability zone in the same region. What this means is that all of the traffic that is being executed on that primary database node, all the I/O for database pages and for wall records or write-ahead log records, and for Postgres commit log and other files, all that I/O will be happening on that primary node to the EBS volume underneath that primary node. And by the way, that EBS volume will always be mirrored, so it's really going to two storage volumes, not one. All that I/O is then sent across the network to the second AZ, and it's executed again on the second AZ to 2 more copies. And because it's synchronous, all of these steps, effectively multiply any sort of latency or jitter. If there's a disk queue or a network queue that slows things down, that's going to get amplified all the way back to the response time of the transaction that's trying to get committed. You can also see how there's all kinds of different I/Os going on here. There's database pages and log records and commit log and other control files. It's really hard to optimize for all these different kinds of I/O. Compare that with the traffic in an Aurora cluster, and it's a very different picture. In Aurora, we have the primary node doing writes to 6 storage locations, but the only kind of writes it's doing are log records. It's not writing all those different kinds of pages and control files and all that. All that information is contained in the log records in a way that allows the storage nodes to reconstruct all those different objects and structures, but that's being done down in the storage nodes. It allows us to make the I/O picture much cleaner and simpler, where the only thing that we're doing is writing those log records. Now the read nodes aren't writing anything because they're attached to the same storage cluster as the primary. So the read nodes read from that storage cluster, but they never write back to it. They also get log records through the network from the primary node to allow them to update the pages they happen to have in memory so that they don't have to keep reading the same page over and over again to get updates. This is just a more efficient way for the read nodes to stay close to in sync with the primary. This architecture, most steps are asynchronous and non-blocking, and so this reduces any kind of jitter or outlier, the effect of outliers on in terms of I/O latency. And when we measure it, you might say, wait, you're doing 6 times more log writes, which we are, but overall there's 9 times less traffic on the network between the database nodes and the storage system. So we're doing more log writes, but a lot less of all the other kinds of I/O. So overall, it's much more efficient architecture. Now, if we take a look down into the storage node itself, and this is a picture of a single storage node, so you can see what's happening. The primary database node sends log records to the storage node. The storage node receives those log records in memory and immediately writes them to a local SSD, a local disk, and then responds back to the database node. That's all it takes to ensure that that transaction is committed, at least for this one storage node. All the other steps on this slide are asynchronous and happen after sending the response back to that database node. All those other steps, are things like, well, let's organize those log records and sort them and filter them and communicate with other storage nodes to make sure we all have the same log records. Oh, and I'll stream them off to S3 too. And then I'll start applying them to data pages, or what we call coalesce on this slide. I'll apply log records to database pages to bring those pages forward in time. I'll always be doing CRC checks to make sure I'm not introducing corruptions, and I'll garbage collect the oldest versions off to S3 as well. But all those steps are asynchronous. They're not in the path, in the latency, in the commit path for those transactions that are trying to commit. And we're using basically disk space to buffer against these spikes in activity. This is all, way below the waterline, not visible to the database or to the end user, but just want to give you a sense of the architecture underneath and how we deliver the performance that I'm going to show you about in the next few slides. One last thing on I/O traffic and replicas. So RDS Postgres has a feature different than MAS, multi-AZ, called read replicas. With read replicas, you can set up a separate full-size copy of your database where we will send all the wall records from the primary to the secondary. That secondary then has to apply those wall records and do all the same writes that the primary did because it's got a separate copy of the database. And so you can see that's not very storage efficient and also not very workload efficient. In Aurora, the read nodes connect to the same node as the primary. the same storage volume as the primary, which means that they don't do any writes. They only do reads. And the updates they receive through the network, they only use to apply to the pages they have in memory. And so in this scenario, it's much more storage efficient. We're not making any extra copies of the database. And it's also much more workload efficient in that the read nodes aren't doing any writes. They're not doing any extra work. They're only supporting reads. And finally, I did mention early on that we also are separating out the cache a bit from that monolithic stack. And so there's a feature in Aurora Postgres called survivable cache. So when an Aurora Postgres instance crashes and we restart that instance, we actually have changed Postgres a little bit so that when it crashes, it doesn't lose its cache. The cache, the page cache that holds the data that's been read into memory by that instance, stays around, and we reuse it as much as possible when you restart the instance. This means that on many crashes, the instance will restart with good performance right away. It won't have to wait. You won't have to wait for all the data to be paged back into memory before you get back up to speed. So survivable cache is a great way to provide better performance and a better experience after an instance crash. All right, so let's look at some graphs of the actual performance as we've tested. And so we did some tests comparing standard Postgres with Aurora Postgres on the same size instances in terms of the client driver and the database instance, but of course with different storage, with Aurora storage on the right and regular EBS storage on the left. And we ran some standard benchmarks such as PgBench, which is a benchmark that comes with Postgres. And so you can see on PgBench, as we increase the number of clients, the throughput for Aurora Postgres continues to climb. Whereas with standard Postgres, it starts to decline or fall down as we add more clients. And so clearly Aurora Postgres is doing a better job of managing large number of clients that are trying to do lots of transactions. And the multiplier is roughly 2 to 1 in this slide. And when we run the same benchmark with SysBench, we see the same kind of shaped curve. And the difference is more than 2x in terms of absolute peak and more than 5x at higher client counts. So you can see again, there's a very good multiplier in terms of throughput for Aurora Postgres as compared with standard Postgres. Now we also, of course, did tests showing the performance of Aurora and standard Postgres as the database size gets bigger. From 10 gig to 30 gig to 100 gig, you can see that the performance of Aurora drops only a little bit as we go to much larger databases. Whereas the throughput for standard Postgres drops quite a bit to the point where the multiplier, the performance multiplier, goes from 1.8x up to 4.4x as the database gets larger. Now this slide compares what we had at the initial announcement last November versus our GA launch basically 10 months later or 11 months later, and we've improved quite a bit on the performance of Aurora Postgres as the database gets larger. Now, of course, to run these benchmarks, you have to load a database first. And in Postgres, you need to, of course, copy data in and build indexes and do a process called vacuum, which is a Postgres maintenance thing that's pretty much required for any kind of major data loads. And vacuum in Aurora Postgres is much, much, much faster for a bunch of detailed reasons I don't have time to get into here. But basically, vacuum touches all the pages that have been loaded and cleans up old transaction IDs, which of course means it dirties up all those pages. And because in Aurora Postgres we never write dirty pages, it's easy to understand why vacuum is much more efficient. And so bottom line is Aurora Postgres will load data 2 to 3 times faster than standard Postgres. And we've seen that data, that result from a lot of customers in testing as well with real world data. Now this graph shows the response time and shows how, and on this graph you want to be as low as possible. You want the response time to be as fast as possible. And you can see Aurora Postgres, not only is the response time faster than standard Postgres, it also has a much narrower range of variability, on the order of 13 times less variable. And so, and this is, a lot of this has to do with the checkpoints that standard Postgres has to do. You can see this checkpoint cycling through the response time graph in blue. Now the other way to look at that data is with throughput, and on this slide we want to be as high as possible, and you can see the Aurora Postgres throughput is significantly higher than standard Postgres and also much less variable. Again, it's a tighter band of performance behavior. And then finally, recovery time. This slide shows several dimensions of data. The x-axis shows writes per second, so more is better, so you want to have more throughput. The y-axis shows recovery time, so you want to be as low as possible on the y-axis. And then the size of the dot is the amount of redo, the amount of log records that need to be applied to recover after crash. And so you can see as Postgres throughput goes up, which means you're separating your checkpoints by longer intervals, recovery time goes up. So you have this trade-off. Whereas Aurora Postgres has no redo to apply. Effectively, recovery time is 3 seconds or less in pretty much all cases. So you have almost no recovery time. It's just a little tiny dot, really. And the throughput is much, much higher, and recovery time is much faster. This is all these results are summarized in this slide, so I won't linger much on this slide, but these are all the data points we just went through. Now, along with Aurora Postgres, we also have added a new feature called Performance Insights. And Performance Insights comes from the initial capabilities we added in early 2016 called Enhanced Monitoring, which gives you access to about 53, I think, OS metrics, up down to 1 second granularity. And this is great, but these are OS metrics. This doesn't tell you what's going on inside your database. And so we know that customers want to see inside their databases as well, and so we've added Performance Insights. This, we have a lot of customers who come to RDS without a lot of database experience, and we need to make it easier for those customers, as well as for the more experienced customers to quickly drill down to what they're looking for. So Performance Insights will, when enabled, will track this new metric called DB load, or database load. And you can see it on your instance list, and you might say, wait, this one instance has got a problem. Let me drill down on that instance. And you'll see a screen that looks something like this, showing the database load, showing the SQL statements that are generating the load, showing the different wait states each SQL statement is in and how much time they're spending in those wait states. And this helps you very quickly find which SQL statements are causing the load over whatever period of time you're focused on. And then you can go and figure out how to tune that SQL statement. Maybe it's missing an index, maybe it needs to be rewritten, maybe it needs other kinds of tuning. But this is a very quick, an intuitive way to drill down on performance problems in your instances. So Performance Insights, like I said, is a feature that's currently available in preview with Aurora Postgres, but we are busy adding Performance Insights to all the other RDS engines, including Aurora MySQL and the other RDS engines. And so finally, I want to quickly talk about how to get your data in. So we have a service called Database Migration Service, or DMS, which is designed to help customers move data from one data source to another. So it might be from, SQL Server to MySQL, or Oracle to Aurora Postgres, or Oracle to SQL Server, or any of these combinations are possible. And we initially launched it with a focus on relational databases, but we've added capabilities for other database sources since then, including data warehouses and Mongo and files in S3 and so on and so forth. Now, customers use DMS both to do one-time migrations. They also use it to do replication, to do ongoing replication. And so there's lots of different uses for DMS. Now, this slide goes through how you can use DMS to keep apps running while you're migrating data. And you start, of course, with a database on premises, and you want to move that database to a database in AWS. Well, the first thing you do is you start an instance of DMS. You connect it to the source and the target databases, and then you can select which subset of your database to replicate. You don't have to replicate the whole thing. And then you turn on DMS, and it will replicate all the tables and data, and et cetera, and keep them in sync indefinitely. And then you can switch over whenever you feel like it. So you don't have to switch over right away. DMS will just keep things in sync until you're ready. So your downtime is however long it takes to switch your apps, and that's it. It's a very short downtime window with DMS. DMS comes with another tool called Schema Conversion Tool, which really is the thing you use first. You have to migrate your schema first and then your data. And so SCT, or Schema Conversion Tool, will give you a detailed assessment report of what it'll take to migrate your specific source database to the target you choose. And so you can run SCT and say, give me the assessment report for migrating from this specific Oracle database to Aurora MySQL, and run it again and get the same report for Aurora Postgres, and compare and contrast and decide which, for that specific database, which is the right target. And so SCT is a really useful tool to help you understand how much work it's going to be to migrate a given database, and to help you choose which target is the best target. And as I mentioned before, SCT and DMS work with lots of different sources and targets, both relational and data warehouses, and we're always adding more to this slide. And finally, as I mentioned earlier on, we did go GA on October 24th with Aurora Postgres. We went GA with pretty much everything you see on the slide. Some of the bullets are highlighted simply because that's what I usually focus on when I'm on this slide. And so I'll just highlight again that Aurora Postgres delivers 2 to 3 times more throughput than standard Postgres. Some workloads it's a lot more than that, at least as reported by customers. Supports up to 15 read nodes. All of them are failover targets, but they are also, of course, usable for scale out of reads. It's fully compatible with Postgres 9.6.3. It also supports all of the extensions we support in standard RDS for Postgres. Works with DMS. And going forward, we plan to continue to stay fully compatible with Postgres as we add support for Postgres later minor releases of 9.6 and Postgres 10. And of course, Aurora Postgres is part of the Aurora family. As you see, Aurora MySQL and Aurora Postgres release new features. Rest assured, we're doing our best to bring both of those versions of Aurora in sync as much as possible with different functionality and features. Finally, if you have any questions, this is how to reach me as the product manager for Aurora Postgres. And of course, there's documentation, and we have a special forum in the AWS forum specifically for Aurora Postgres. Thank you, everyone, for taking the time to attend this webinar.